Okay, I mean, so a very welcome to Professor Kashefi. Actually, she is well known to this center. Unfortunately, the director, Professor Das, is not here. He has to go out because of a prior commitment. Okay. But obviously, he will listen to your talk because it is on YouTube. So, can you hear us? Hello?
Yes,
Can
yes. Hello, hello, hello. Yes, I hear you. Thank you.
thank you. So I think we are just going to start in few minutes. Okay, so I think we are just about to start. So okay, so it is a privilege to have a distinguished computer scientist, Professor Elham Kashefi, as a speaker to celebrate IYQ at the TCG Crest, Kolkata. Professor Kashefi he is known to this center. He has had online meetings with our director, Professor Das, and some of the faculty members. So the Professor Kashefi received her bachelor and master's degree from Sharif Institute of Technology, Iran. She obtained PhD degree from Imperial College, London. She has held various positions at University of Oxford, University of Waterloo, and MIT. She joined University of Edinburgh in 2007. Currently, she holds a personal chair at the University of Edinburgh and is the director of research at CNRS, Sorbonne University in France. She is also National Quantum Computing Center, which is based at University of Edinburgh. She is chief scientist there. Actually, she is one of the founders of the field of blind quantum computing. She is K in the famous BFK algorithm. He has also made pioneering contributions to the field of quantum cryptography, verification of quantum computing, and cloud quantum computing. Her research spans from foundation to industrial application. I now request Professor Kashefi to deliver her IYQ lecture, Distributed Quantum Computing as Professor. So, Professor Kashefi.
Thank you so much for the invitation and this kind introduction. So yeah, I'm actually going to talk a little bit about all those topics you covered, but hopefully giving you a little bit of overview of the field as it grows, as well as the recent progress. But I guess we can all start from the celebration that we are all very excited after our pioneer who have been recognized in the field a few days ago, and is all about how quantum computing is become a reality thanks to these pioneers. So I want to now address, now that we have reached to here, how does the future is going to look like, and some of the challenges that when we let me make this one small so it doesn't cover it. So when we're thinking about the scaling up quantum computing and making it really as a service for everybody, these are challenges that I like to share with you and shed a bit of a light of how they can be addressed. And feel free to stop in the middle if you want to have a discussion right as we go forward. But I don't see the screen, so you need to make me aware. Okay, so what are these challenges? The scalability, privacy, integrity, utility. Let me just go quickly through them just to make sure we are all in the same page. Of course, we need to scale up all our qubit, the qubit scalability. This is the one roadmap from Google, but everybody's aware of it that we're requiring many, 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 many physical qubits in order to achieve. So the hardware need to scale up. But it's also, we have issue of scalability regarding the user. We want to ensure that several users will have access, and that's the architecture that Amazon Quantum Network is trying to reconstruct, that how we are making sure the various users can also connect to the quantum platform that we are developing. The two other challenges that I will focus more, if you wish, you can be saying it is more on the application side, is the issue of the privacy first. Well, we know in modern data science, everything is about distributed computing. Any application you can think of, fraud detection, synthetic data, machine learning, training, digital asset, stress test, these will be always about distributed. Data is distributed, computation is distributed, platforms are distributed. And here the issue of privacy is very important in the classical context because you have regulation versus data sharing. And this become more and more clear with all the drama we're seeing from OpenAI, etc., that we cannot easily do whatever we want to do without respecting privacy. And that would be a challenge also for quantum computing. And another challenge that also even exists in classical, but in quantum become even more important is that the integrity, verifiability of a computation. In case of quantum, we always have this drama that have we really achieved quantum advantage, or is there is still a classical simulatable scenario because we don't know our devices are so noisy. Even when you have a very fault tolerant architecture in future, you still need to have some notion of verifiability that all the assumption we made for our fault tolerant architecture is still are in place. So hence we can really claim we have achieved quantum advantage. So correct functioning of scalable device as we're trying to scale them to the million and beyond qubits is another issue that we need to deal with. So these are the challenges that I mentioned. And since, and of course, the utility, very important challenge on its own. For example, just focus on quantum machine learning. We have a lot of debate going on. Is it really there is a quantum advantage or not? And there's lots of issues that need to be dealt with. The quantum machine learning that are trainable, the quantum machine that are expressible, and yet they have no classical simulatability. So to me, these are the ongoing challenges that many researchers across the world, including in our team, are addressing. And my message in a very overall view is assuming it's just giving you, like any physicist, a fundamental equation. So it's very important to say that the message of my talk is that, in fact, these challenges that somehow seems they are not relevant, utility in quantum machine learning, scalability of the hardware, integrity against the noise, and privacy in terms of the crypto security. But they are all actually, in my view, they are the same challenge in the sense that, maybe now I correct myself, it's not same challenge, they can be addressed at the same time. And that's my point of the distributed architecture and using quantum communication. And depending on which field I'm giving this talk, sometimes I'm saying that you can look at them giving quantum communication. Sometimes the concept is adaptivity of the architecture. Sometimes essentially is mid-circuit measurement, sometimes network QC. In fact, all this notion, quantum communication, adaptive architecture, mid-circuit measurement, network QC, these are another way that I want to emphasize that right now that we are designing this platform from the hardware point of view, we should take care of adding the layer from the software point of view. So that's the overall picture. Let me emphasize it more because probably understanding the question is more interesting before I show you the solution. To me, the most interesting way is that these issues that I was saying, accuracy, privacy, integrity, synchrony, these are issues that we're dealing in a distributed architecture, even in a classical network. And usually, because the way that the internet and the classical computing has evolved, these are always a software-based solution on the top of the stack. Okay, there are issues that they are not quantum safe, but even if we put that aside, because the classical bits are very easy, they are free, and this architecture existed even before all this application comes to the fulfillment, like what we're seeing with the progress of AI. most of the time, if you see in the current trend, everybody is trying to add a patch, a layer to address now privacy, now to address accuracy, now to address synchrony. Whereas in quantum, we have the advantage that we are building this distributed architecture now. We are building quantum internet now. So, and on top of that, we have quantum link. So it's a very, very different, the distributed architecture when you're putting them to some extent. Okay, they are classical devices and you're creating GPU, CPU, all of these HPC center in a various model. But in the quantum case, we have advantage that we are quantumly linking. And I want to argue that this opportunity that we can address all these challenges, both from software side and the hardware side, as well as already design it to be quantum safe, is the main message. And hence what I was showing you, the privacy, integrity, scalability, they all can be addressed at the same time as we are building. So let me just put the picture of the main picture, and then I essentially start my talk. So we have a blueprint, and this comes out of many, many years and decades of work we have been doing, that they were individual protocol, if you wish. You mentioned already blind QC, verification, and various other work we have been doing. And then we try to put all this protocol, optimizing them according to the roadmap, the hardware. So that's the blueprint that now we are believing in and we are pushing forward, is that while our hardware partner, whether commercial or the experimental lab, are designing distributed platform, because distributed platform is the key to how to address fault tolerant architecture, etc. We are showing that how at the level of design, you can integrate this client server protocol, and that's exactly the blueprint. And then hopefully I can convince you that this module architecture that is for the single client and server will solve the problem. It's easily scalable to provide it in the multi-setting, which is ultimately what we want to do. So for me, the message for today is just really showing that how, after doing all of this research, we figure out the component, and that component is the only thing need to be added, because the rest can be layer in terms of the software layer. So this is the hardware software layer. So I'm going to quickly show you what is this new protocol that we have designed. Is the most optimal protocol that we have for the scenario that you have one client and one distributed server and you want to achieve privacy and integrity. And then I show you how the same model, same architecture can be extended to multi-client. I will argue what is this building block that we have now identified as the only thing that the hardware people need to accommodate in their design. And then, if time permitting, that probably I don't get it, I also show that how this is also a building block for the machine learning enhancement that we have been exploring. Since I'm not going to go through all of this thing, I just flashing all the relevant publication that the story is built on that. So it's a very collaborative work with many colleagues and collaborators across several teams. I will refer to all this work again, but again, I wanted to acknowledge all the work of everyone to make it possible. So a bit of brief history of the field, just to make sure we are all in the same page. So we are talking all the framework that I'm designing this solution is distributed quantum computing, or a more precisely measure-based quantum computing. Measure-based quantum computing was introduced by Robert Rosenthal and Hans Briegel in 2001. And it was an alternative architecture compared to the gate-based model or adiabatic annealing model for, if you wish, initially for the hardware solution, designed for photonic or even cold atom creation of computation, that you have a massive entanglement and then locally using LOCC operator, you're able to manipulate and come up with a universal machine. Then it was very soon shown that it actually very suitable for photonic. Is one of the first experimental demo for this MBQC was by another Nobel Prize winner, Anton Zeilinger and his team, that they showed that how element like KLM and all the post-selection, etc., can be nicely implement MBQC. We worked also immediately in order to create a very abstract language, in order to forget about a very hardware structure, but creating, if you wish, an assembly language for this distributed computation, which was called measurement calculus. But this path, I mean, I'm not showing you millions and many other contributions by many researchers, but the important that this is now the foundation of a commercial available photonic computation. Xanadu, Orca, Quix, Quandela, PsiQuantum, they are all built based on this variation of measure-based computing or boson sampling computing or fusion-based computing. But that's exactly an architecture that naturally has the distributed computation in it. And that's why that will be the basis of a lot of things we say, because it is the roadmap that we are saying that is towards fault tolerant. In parallel to this hardware progress, if you wish, there was a challenging question that was raised also by Scott Aronson and in a beautiful paper by Vazirani Aharonov quite almost 2 decades ago, that they said that, okay, while we're building this scalable quantum computing, we eventually reaching to the regime that we no longer know what these machines are doing. And is quantum computing or even quantum mechanics is falsifiable? Can we really test the outcome of a quantum computer that is beyond the capacity of classical computer and be able to say about its correctness? And that's the field of blind quantum computing with my colleague Anne Brodman and Joe Fitzsimon in 2009 that we proposed this protocol. And the first proof of concept again with Anton Seiling and Philip Walder's team demonstrated, and some other pioneer work like this work on the entangled regime was also proposed, and we have shown this. So what I'm trying to show is like in the top, well, quantum computing and MBQC as a platform has become commercial and has advanced. Recently, I would say for another or up to the last few years, we still explore it in a very theoretical way. All the protocol, despite the POC that we were presenting, they were not catching up with the hardware progress. And that's the novelty that I want to present later on, that while in theory and paper, in many results, we demonstrated this verifiability, integrity, privacy, but the gap between theory and hardware has been so much that essentially there has been a POC. It has not yet been integrated in a commercial platform. Just before I finish with the history, there is parallel to all of these things. These were all the scenario of one platform and one client. But the quantum internet has been a very active field in our research. There is this pioneer work by Werner Elkos and Hanson, which actually put forward what is the roadmap for quantum internet, how new layer of quantum is expanding, how new building blocks are coming. And again, in theory, they also demonstrated the multi-client secure quantum computing, which is exactly ultimately what we want to have, that our data, our computation, our structure, everything is distributed and private and verified. And some proof of concept of those are also demonstrated in Hanson Group. And that's exactly the foundation of a very active research in Europe, in UK and elsewhere, which is called quantum internet or quantum network computation. And I think fast forward the story, I want to bring you to our latest work that we believe, putting all these bits and pieces, we are able to actually show that all these components that has been always explored theoretically are now so close to the roadmap of quantum network and quantum computing platform that even commercial company like Very Cloud, which is my own company I co-founded, we believing this thing is something that we can start unrolling in the few years rather than forever remaining a theoretical work. So that's the overall picture. And now I'm going to move you to start giving you some element of this protocol. I'm not sure everybody is familiar, but more importantly, rather than going through the math, I want to give you the component to demonstrate what is the new progress that we have made that made those theoretical work so practical with the existing. So I'm going to tell you the story in this way. So first, just to make sure that we are seeing it, let's run this particular example. So this is what we call graph state. So there is all these gray nodes. They are essentially single qubit, and they are entangled using a control Z interaction. So that's something that you might have heard as a graph state or a cluster state, and is the basis of a measure-based computing. So in a normal setting, when you don't think about privacy, integrity, etc., you usually set up such a graph state. Then for each one of these particular qubit, you will measure them in a particular angle, let's say in the XY plane, and based on the classical outcome, you will decide what will be the next one. So in an architecture, when the server is the perfect, without any noise, without any problem, and the client are completely trusting and there is no privacy of the data, the construction is very simple. Essentially, a client using classical computer and classical communication will instruct a server to create for its computation a particular graph, a computer as architecture, and the program are these alpha 1, alpha 2, alpha 3. So now I was talking about distributed quantum computing, and of course, this cluster state might be sitting in just one lab or in one place, but you can easily see the roadmap, for example, Psi-quantum roadmap that they are building this fault-tolerant architecture. These devices, you suddenly can look at this circle rather than being one qubit, will be one quantum module. So you might have 100 qubit in this gray area, which is your local node. And then you create quantum link. These are the things that I'm highlighting to entangle them. So for our purposes, I just want to emphasize that when you're talking about the scalability of the qubit architecture, you're already thinking about this quantum link between nodes, between different servers, in order to increase the size of your graph estate so that not all of them are in one place when you're talking about 1 million. So that's when you're just thinking about distributed quantum computing. In fact, it doesn't matter if you build it with the photon or you build it with the cold atom or you build it with the ion trap. The only thing that is important that you can construct such a resources that we require. And in this paper, as I mentioned, is like this is a programming language, an abstract language that we define for distributed based quantum computation that we can to some extent abstract from the hardware, whatever qubit it is, but yet staying very close in terms of the instruction, the resources to be prepared, the architecture of the resource, the classical instruction from client to be sent to the server, and the manipulation of the data. And even in a bit more abstraction of it further away is another work by our colleague from Edinburgh who's coming out soon, which is they even make it more heterogeneous, that maybe some part is MBQC, some part is circuit-based, sometimes is with a different type of platform. But abstractly, we can from now on forget about the qubit and really thinking about this graph that we're going to play with. Okay, so far so good. We are sending the instruction, we're running our program, we're going forward, and now we want to address the first challenge. The first challenge is that these devices are going to be noisy. So you can think of them either the server being malicious in terms of trying to learn our data and we need to protect it, or you can think of the server being noisy because they are not perfect or we're not sure the fault tolerant architecture works or if they are NISQ area. In either scenario, whether the server is actively malicious or being noisy, we can essentially consider that we need to provide privacy. And this is an interesting model because whether you're coming from the design principle that you want to ensure the noise has not destroyed your computation and hence you can mitigate it, or you're coming from the application point of view that you want to do privacy, we are treating any deviation, whether it's noise deviation or computation deviation, as the same, and we're providing the strongest possible privacy against such a noise. So now, how do we do this? So what do I change? I will keep the same graph and each time I show you what I'm adding on top of it. The only thing you add is that the architecture is still the same. You have a link between your server, the graph is the same. The only novel thing here is that now, instead of asking the server to prepare the plus state or any qubit that is preparing itself and then continue the procedure, we can ask some other potentially the server, malicious server, etc., prepare a qubit, and that qubit is coming to our lab. We are the client. And we just need to randomize that qubit. So you see this device that I'm designing. I don't know if you see my arrow. So this quantum state could be any state, could be entangled or not, could be what we believe it should be or not. It could be malicious, it could be noisy. It comes to this trusted environment, which is in the control of the client. And client only need to decide a random rotation of the form, Pauli X random rotation or Pauli Z random rotation at putting it, and it send it back. So this is now, if you wish, a mini quantum computer on the server side is a random rotation, and we come to the implementation of it. But the very interesting thing is that I don't make any trust anymore whether the server really has this architecture, whether it has a Markovian noise, etc., whether they are entangled or not. I'm just making assumption that this red box is in the control of the client. Client can ensure that in this environment, we have introduced the rotation that we wanted to have, and it doesn't care about preparation, it doesn't care about measurement, it doesn't care about anything else. So to us, this is the latest results we have had. This is the minimal amount of trust that we need to have in order to enhance scenario in such a way that we are protecting against the general quantum. So now, instead of client only dealing with the classical instruction, if you can see, it also have a control of that building block, which if you wish is a quantum instruction. So here's now I'm introducing a new aspect of distributed architecture. There need to be also quantum link between client and server. So in a normal distributed computation, you just have the server and you're putting them and you're linking them. Whereas in the scenario that we are dealing with, hence quantum internet, hence distributed, hence quantum communication, you need to also provide link between client server, but client doesn't need to have a full access to quantum computer or the resource or the measurement. It just need to have access to a rotation box. That is, now we can discuss it in a second, how it's built. Okay, I hope you're following me so far. And that's essentially the only building block that we keep now reusing it to answer the privacy, scalability, etc. the question. And of course, we don't need to do this just for one qubit. We need to do it for all the qubit. So now, any computation that is involved in our graph, in this case, we say a 5-qubit computation, but now imagine it's a 1,000,000 qubit computation. All those qubits need to go through this randomization. In fact, I pose here a side remark that depending on the level of the noise, depending on the level of your privacy, you can compromise in the sense that you don't need to have all your qubit to be randomized. But for the sake of argument, let's say that we have this quantum link between client and server that I was mentioning. And every time that I want to upload the computation, before I upload it, I randomize it, exactly like a QKD masking. And then from there, I benefit from this hardware software. So you see, all these dotted link are the classical instruction, which is essentially the protocol description of what do I need to do. And all these instruction are doing is that you have randomized, hence this alpha one is one-time padded, but you need to compensate about it. And that's exactly the classical computation that client is doing. So all of this thing together is this latest work that we put verification of quantum computing without trusted preparation and measurement, which is essential element because it made all of our protocol very, very much optimized and minimal overhead on top of what the hardware people are doing. We are only telling them when you're building your distributed architecture, ensure that you're also creating an access point for a client server link because you anyway are building. So it could be that some of this node are now client node. The entire thing is a server node, but some of these nodes become client node. We can think about that. But the main element that changed the game is the simplicity that just this rotation on the angle of computation allow us to achieve what we wanted to achieve. And this maybe the privacy is very easy to be seen in the sense that, okay, before we were telling the server, the program, which has this magical parameter alpha 1, alpha 2, and for some of them you get Shor's, for some of them you get in Grover, for some of them you get a quantum chemistry problem. So those parameters are essentially the only thing that define your algorithm or your program. And now I'm randomizing it. So it's very natural that, okay, I randomize, and now the collective phase of randomization in the boxes plus that will define what is the program. And because only client knows it, so the server has no clue which algorithm is running. So privacy, to more or less, is trivial and is easy. Of course, you need to prove it. But maybe integrity is a bit more tricky, but let me tell you how we also achieve not only the privacy of computation, but ensuring that server is exactly doing what we're telling them. So we have this magical box by this coloring, by this communication, that essentially server doesn't know what it's trying to do. So we take advantage of this and we are updating our algorithm or protocol or the software layer, if you wish, that sometimes our computation is a computation. This is exactly, when I'm putting it gray, means that this is exactly, you have randomized it, you have put the masking, but the algorithm that the semantically you're implementing is exactly your quantum chemistry simulation, is whatever problem you have in mind, which is probabilistic, meaning that you have no clue what is the outcome because it's not classically simulatable. Here is a 5 qubit, but imagine this is the architecture of my 1 million qubit machine that I'm using it for some, I don't know, some quantum chemistry simulation, eigenstate calculation, etc. And now I have no clue whether I'm doing it or not. So I keep those still masked from the server, but what I can do, use the same architecture, exactly the same architecture, connectivity, etc., to create what we call a test run. And the test run are very special because we put them in such a way that some of those qubit measurements become deterministic. In general, this computation, they are all entangled. So every qubit, the answer 0, 1, they are both correct, and they are the probabilistic nature of our computation. Whereas in the test run, I'm designing it in such a way, and this is the whole details I'm putting under the carpet, but simply putting it is that in such a way that from server's point of view, it doesn't know that I am in the compute run or in test run. Whereas for the test run, the client know exactly what is the expected outcome. And then what we show is that if you run several shots of the computation, so there is no overhead in terms of the number of qubits. It's not like a fault tolerant computing that if you want to do a computation over the, let's say, 100 logical qubit, you need 1 million physical qubit. No, if you're giving me few physical qubit, I always work with physical qubit, but I have several shots. Sometimes I'm doing computation, that's great. Sometimes I'm doing this trap, which are designed in a very particular way, uh, such that, you know, the red qubit have deterministic outcome, and we don't care about the green qubit. But the main point is that a server, a noisy device, a malicious adversary cannot distinguish whether I'm doing great computation or one of these colorful computation. And that allows us to have the strongest possible error detection. Essentially, we are able to look at the result of the outcome from this colorful point. If they are the way that we want to be, we have proven it in the strongest way using abstract cryptography that they guarantee the correctness of your gray computation. And that's a very beautiful thing. So I'm testing over the different shot of the computation, but unlike error mitigation or any other characterization, because of the privacy, because of the hidden computation that I have created, it guarantee of the correctness of my gray computation. I can talk about that forever, but let's move on. So essentially, this framework, it allowed to use the cryptographic technique such that any global noise that your device can go, it could be non-Markovian, it could be in any scenario that you can say without any assumption about the power of adversary, just by ensuring that my trap computation are giving me correct result, I'm ensuring the gray computation are correct. And in fact, I'm taking the majority vote and it's boosting, so you're also getting exponential guarantee in your correctness. So now I can run various computation and get a confirmation about the correctness of them. And this appears in this set of paper, and I will talk about the experimental demonstration of it. So that's it essentially. So now, while we kept the same architecture that I was showing you before, so that's the whole point. So it's the same thing. The experimentalists and platform hardware are building it. We're just adding the quantum link between client server. And now what do I do when I have such a quantum link is become software. So that was my quantum part, quantum link, but the same software can update to give me privacy, and the same software can update to give me verifiability. Now you might ask, okay, so far so good, but what if I have several clients and in scenario that even the client is malicious? So here's come the real pitch that I was showing you, that we are in the distributed setting. Think of it, I don't know, you're trying to do machine learning. Your data is the data of your client. They want to keep the client, they want data to be private. Somebody is designing a particular transformer architecture. They want to design it in such a way that that architecture is private to them and is not leaked. And somebody is the hardware provider and they want to even keep some aspect of the hardware private. So in this scenario that now nobody trusts anybody, client could be malicious, the server could be malicious, we need to add another layer, but this layer is still remains software layer. So let's go through it. So before, in this setting, each qubit was randomized by the same client. The same client was randomizing every computation and was orchestrating the whole thing. Now we have the issue that there is several clients, client one has part of the data, client two has some other part of the algorithm. Think of it like a federated machine learning, that you want everybody locally bring their data, but nobody wants to leak their data to somebody else. So now in that setting, it's again is not changing. And this was again take us a lot of work to redesign it in such a way that the same platform, the same structure, but the only thing that is happening in here now, every client need to randomize every qubit, even if it's not related to their part of the computation. So here now we have quantum link between all the client and all the server. So instead of being one client and one server having a link, they all need to introduce this randomization that I was telling you. And then what about the classical part? What about the classical orchestration? Because they don't even want to classically communicate their data together. And that's where the classical secure multi-party computing comes to the picture. So we already know how to deal with the distributed computation, privacy preserving in the classical world. And that's the only software layer we need to put for our communication. And then for the quantum part, we only need to add this masking over and over. So for me, the fact that the whole thing in modular building on top of each other is the key message. I mean, of course, I'm not showing you the details of the protocol. Most of the time, the same technique, the same proof technique goes through, but the simplicity of what are the new hardware element and what are the new software element is the emphasis of my talk. So now, finally, we have what I was pitching you at the beginning. We have multi-client, distributed, private, and verifiable measure-based quantum computing align with the roadmap of how am I building my hardware. So every time we're talking with, I don't know, INQ, or we're talking to various architecture, photonic platform, we just need to know that how are they building this platform? What are this distribution of the quantum link that they are envisioning? And then identify where we can put the quantum link for the client to come to the picture, and the rest is become a software solution. And then we actually demonstrated it in together with the colleague, the Fabio Schiano group at Rome, that we actually put all these bits and pieces to demonstrate, compared to the very original POC that was way more demanding on the hardware, what are these components? So this is exactly what I was showing, and this is a pure photonic platform. So you can imagine here's the server one, which has the source and is creating entangled photon source using parametric time conversion, but we have no trust to it, in the sense that this source could be very noisy, it sometimes create entangled pairs, sometimes it doesn't, but that doesn't matter. So that's the server. And the other part of a server, if you wish, is a distributed server. And here, of course, is making a measurement and adaptive measurement, etc. This is the POC, but you can think of it now, I have several sources, several measurements, several architecture. But what is it the client need to do in order to achieve everything I was showing is that when this photon goes from one server to the other server, the client just need to apply a random rotation. And in this case, of course, is a polarization, because we're using the polarization encoding. And that's it. So now my client, Alice and Bob, they don't even need to trust each other. They don't need to trust anybody. They locally randomizing every qubit. So now every qubit, before it starts running a computation, has got a mask from all the client. It's like a secret sharing protocol. So everybody has contributed to this secret sharing. Everything has been masked. And now using this digital circuit, is this trusted TTP which could be in general in a secure multi-party computation, but in order to deal with the photon loss, we just assume that we have a hardware secure classical module, which is essentially orchestrating it. So here's the hardware component and here's the software component. And now these two servers cannot know at all what is the computation. On top of that, the client can test whether computation is done or it's been too noisy or it's been tampered with. Let me not go through the state injection regarding photonic because I just want to have enough time for the discussion. But this is really wrapping up the structure of how we're putting all the components together. This is the picture of the distributed computing. And there is lots of, I mean, while I'm showing it, that is like as if it's done, but there's lots of other question that is remaining regarding every component. How do we building it? How do we go? And I want to quickly showing you a little bit of a perspective and then stop giving time for the question. So, okay, we have this building block together. And as I mentioned, so the only component that you need to have is the component of the this rotation. So but forever there is room for optimization. You know, this trap design that I show you, this colorful graph, still there are several run, and we are believing we can even simplify them further and further. And there is a beautiful link between error detection, error correction, and this trapification technique. If you're interested, you can see in this work. There is something that I jump quickly on top of it, is that we want to really link it to the quantum machine learning. Now, in this architecture that we have recently designed, which is a photonic architecture for convolutional neural network, the design is completely based on photonic, and component that is here is allow us to bring our privacy preserving blind computing that I was showing you into this picture. So now, really, in order to do that, we need to deal with, you don't want to randomize everything. That's what I mentioned before. You don't want to make sure that every single computation and qubit is randomized because it affects the noise, it affects the correctness. So in a very recent set of work that we have put out, we demonstrated how we can have partial blindness depending on the particular application for machine learning, that it's enough to provide for us the privacy, but you will lose the verifiability. So there's lots of open question here, that can I take some of this component of that I was presenting you, adopting them, and yet achieve the strong result? We don't know. This partial blindness and partial verifiability is a very interesting open question. This is the also maybe people with the hardware design mind. It's like, it's also every time to understand where do we put this masking layer. I show you that component. In the case of photonic, this is very easy. So you put various sources, they are not trusted. You put the little rotation, the polarization rotation, and that's easily adapted to a scalable architecture. But what if I'm working in a very different platform? This is like a AWS architecture, that they have a very different model for the interconnecting their qubits, and we need to readjust. For example, how do they look at this quantum link orchestrator? How do I add the masking? Or in the UK, there is this ion trap photonic link that has been explored. And the way that the link between ion trap are done is using a post-selection on this photon that is emitted from two different ion trap. And now we need to add our masking here. So depending, while I claim that, okay, we have adjusted to the hardware roadmap, it's a strong claim. Every time we need to really looking at this roadmap and identify where can I translate my box that is just a rotation, that mapping in the correct way to their hardware architecture. So we have done it for the ion trap. This was a demonstration with the David Lucas lab, that indeed they have this ion trap, and from in this ion trap, a photon can be emitted, and that photon become the place that we can measure it in order to introduce randomization that we require in our computation. So the architecture is slightly different. It's not a single rotation. In fact, the trusted measurement that we have put. But every time is a job and is an exciting project to figure out what are the components available in a particular platform that allow us to translate our work. Some other work that we have done is we work with the Quantinuum, and there is no quantum link between client server, but they have isolated gate zone. And they design it interestingly for fault tolerant quantum computing, but we have managed to translate our framework of the verifiable computation to this isolated gate zone. So we treat this isolated gate zone as the zone that the client can have access and randomize. And using that, we are verifying the entire computation. And that's because it's the superconducting qubit are the qubit of the day due to the Nobel Prize. I'm also very, very keen to see how we can work with superconducting platform. And that's the trickiest one because the distributed architecture need to explore, for example, how this coupler between qubit are activating. And then we want to add the masking there. I have no idea how to do it. Some other colleague also look at the weak coherent pulses as an alternative to take it to the CV platform. And in general, essentially to finish is that this is the box. This is all we need from our hardware partner to give us an access to so that everything outside this box could be noisy, could be untrusted, could be malicious, but we want to make sure everything inside can be on our control. And in fact, more precisely, it's not like exactly need to be our control. We just want to make sure the noise of this device, that is the randomization of a single photon, if a single qubit, is independent of the secret theta that will leak out. So you could have a noise everywhere, but as long as you guarantee my secret rotation inside this box has not leaked to the outside, we are game. We can build all of our framework, etc. So essentially, if the noise of my random rotation remain independent of the theta, then we can show the entire framework goes forward. But that sometimes could be tricky and we can discuss it. Maybe I stop here. There is lots of other questions, but depending if the question comes, we can discuss it. But that's it. Thank you for listening.
Okay, so thank you very much, for this wonderful talk. So let me see if we have this here. Okay, so I have one question. So you are introducing this quantum link, right, between client and server, right? So
Correct.
so here this our client can be purely classical, or it still has to have some quantum capability so that your content so that computation is private.
No, a client needs to have some quantum capability. And that's actually a very interesting open question. We have not, well, let's put it this way. I strongly believe to achieve this blindness and this verifiability, you cannot achieve it with a pure classical client unless you also put the condition like the pioneer work of Mahadev, because they also introduce alternative way that if you're happy to limit the power of the server to be not able to solve problem like lattice-based cryptography, then you can use technique from post-quantum cryptography to make the client purely classical, so you don't need any more this quantum link. So that's one alternative way to go. So the comparison is that either you go with post-quantum and hence, well, okay, your security framework is only computational secure, but there is also a caveat to that is that the number of qubits that then you require on the server, the overhead of server becomes huge. So if you're really talking about with the NISQI device or maybe with whatever device that we are merging, we want the cost of privacy in terms of qubit not to be overloaded, then I believe we need to have this quantum link. So it's a bit of a choice. Either we will have very strong fault tolerant machine that we don't care with the number of qubit, and I don't know when we will have those machine, then we can deal with the pure classical client in a post-quantum regime. Or we will provide this quantum link, and that quantum link with the minimal capability for a client, which is just single qubit rotation, allow us to achieve this privacy.
Okay, okay. So I mean, does this privacy also will introduce some extra overhead? Say for example, I mean, for fault tolerance, we increase number of physical qubits that are required manifold, right? Now you have extra requirement of privacy, right? So will that increase the number of physical qubits that might be required?
It's a very good point, but that's what I wanted to emphasize. So the overhead that the privacy or verifiability is introducing is not in the number of qubit, is in the number of round of computation. So if I have a device tomorrow that is, let's say that is a 1000 qubit device, and now you want me, unless that you have provided this quantum link to me between my client device and this server, I will never want you to give me more than 1000 qubit, but I will run, instead of one run of computation, I will run several. And this is not very complicated because we know that due to the architecture that we have, we will, anybody who runs is always, you have several shots. But the cost of now privacy is that you need to run even more shots. And depending on how private you want to be, that could be the overhead, but it's always polynomial overhead. So you see, so usually if you were running a new computation, you will run only this gray shot, and then you take some average or you do some error mitigation on top of it. Now, the cost of privacy is saying, okay, you need to bring some more randomization. Those randomization is also linear in proportion, usually linear many more, but there are only several more shots. And those are the where I can guarantee my verifiability. And so let me answer your question. For if you only want to have privacy, the only cost is the quantum link. You don't need any more extra physical qubit. You just need to give me a quantum link, and quantum link compile the same algorithm exactly as it is. If you want to add verifiability on top of privacy, then you need to run several more shots, but those more shots are linear in the size of your computation. So we never need as many qubits as required for fault tolerance. So this is exactly what you're asking, essentially the huge difference, compared to the protocol we defined almost 20 years ago, 10 years ago, and protocol we defined. And the protocol and the task is still the same, but we managed to remove all this overhead for the scenario that your problem is a classical problem and is a decision problem. So that's another thing. If you still have a quantum problem with quantum input, quantum output, that's require extra overhead. But now we have reduced this physical qubit overhead.
Factors.
Sorry, I don't hear at all. I think somebody's talking. I didn't hear at all the question. Maybe you need to come to the.
Okay, I'm repeating.
Okay, thank you.
Alpha 1 to alpha 5, you showed that you said that each one could be 1 qubit, or it could be even 100 qubit. So if it is
Correct.
qubit alpha 1 and 100 qubit alpha 2, so do you have all-to-all entanglement in that case?
Very good question. I would say that the architecture that you require is depending on your algorithm. Of course, you don't want to have all-to-all entanglement. So let me bring this. So this is a little bit of independent of the privacy. So when I'm showing this, what is this graph and what is required? It's the entire field of like a circuit netting and algorithm compilation. So I would say that you will create, let's say that like there's 100 qubit here, another 100 qubit here. Usually people don't want everything is connected. You want to decompose your algorithm in such a way that you require few quantum link between servers and many link within that architecture. So that aspect, it doesn't change our story regarding blindness or etc. to some extent, because we need to still randomizing it. But what is the requirement for those connectivity you're asking? It depends your algorithm. Sometimes the algorithm is require a graph that is everything is connected. Sometimes an algorithm requires something is simple, and there is beautiful set of work that people are dealing with how to distribute. So you give me a monologue algorithm and you want to distribute it on this distributed setting, what is the best way to reconnect? But regarding privacy or verifiability, that's not changing. We will work with whatever graph that is already implementing our algorithm. We're just adding a layer for privacy on top of it.
Okay, thank you.
Hello. actually, I have a question on the security. So in your distributed quantum computing architecture, how you actually ensure the composable security?
It's a very good question. So we prove all of our framework in the, did I put some slide, in the abstract crypto. Let's see. And now I removed it. So the framework of this proof is started. So there is for the very first protocol, before any of this optimized protocol I show you, there is a beautiful work by Fitzsimon, Dunjko, Portman, and Renato René, that they already introduced how you can use the framework abstract cryptography to design composable security proof for the client server. And that is essentially the scenario, without going through too much detail, is that you define an ideal functionality, which is almost like the boxes I'm showing you, ideal functionality that I want, I give the input to my alpha I, alpha n, and I want the output to be the algorithm, but I want nothing to be leaked. And then you design a simulator to ensure that the real protocol is indistinguishable from the ideal protocol. And then they demonstrated, in order to achieve this composable security, there is some local criteria, few standalone condition that if your protocol satisfy, you can uplift and get the composable security. So that's become like the Bible for all of this security. Almost any paper since then that we have written regarding verifiability, whether we change some of the component, we define ideal functionality, we define the simulator, we show that all those criteria is satisfied, and this way we get the composable security. And it's very important that we're showing it in composable security, because all those bootstrapping, the question were asked before, that how do you ensure the overhead is not and you're still achieving the security, is because of this composability. It means that the run, which is the test run or computation run, does not be distinguished, and we have composability. So in the abstract crypto framework, we prove that security.
Also, a classical client, how can the client actually test the result? I mean, is there any device independent way to check the result if it is, true or false?
In the scenario that when we have a classical client,
yes.
So in our protocol, you're right, the protocol is not device independent because the client has this. Let me bring to clarify. So when you go here, if you see, we are assuming that this device is properly functioning in the sense that I have implemented rotation. If you wish, it's almost like in the QKD, it's not device independent QKD, but it is I wouldn't say prepare and send. It's more kind of like not receive and measure is the other one. What you say, like measurements. Anyway, is another version that I'm trusting. That's why I say it's a trusted single qubit rotation module. So it's not device independent. So this client is making sure this is trustedly preparing. And then in order to check the correctness of outcome is, as I was saying, you just need to check this outcome measurement are correct, and hence the rest is correct. Now, if you want to make a device independent version of it, and it exists a device independent version, and when I was showing you this version, so the work by the original work of RUV, it creates two entangled server, and there you run the Bell inequality, and you can create a device independent version. And then very recently, a work called Verifier Unleash actually defined a very, very optimized version of this thing that you can do everything that I was demonstrating you by doing self-testing and run a device independent. But there, as usual, you need to make an assumption that you have two entangled server while these server are not communicating. So that's the only thing you can do. So you have two malicious party, which are server 1 and server 2. They are entangled, but they are not allowed to classically communicate. And then you can bring all the theory of self-testing and Bell inequality to achieve device independence. To me, I think it's a very important theoretical work, but enforcing that two servers are not classically communicating in a malicious setting is a bit unrealistic, but it's much easier maybe compared to the client link between the client and server, but they are both protocol existing.
So do you think this can be extended like for multi-server system? I mean, this device independent scenario which you have mentioned just now.
Good question. I think so. I have not seen it. So it's like both our protocol and Dolek et al. Protocols, assuming client have some local quantum capability, uplifting all of those quantum capability to the server. I think it's doable, especially with the recent work that I was showing you this one. So in our work, the multi-client, where did I go? Sorry. Yeah. So now the only thing that the client are doing are this rotation. So now uplifting in such a way that these elements are again tested using self-testing, it is a possibility. It's a bit of a headache because nobody's trusting anybody here, but probably it can be done. If again we compose that no client and no server can have classical communication among themselves, then probably we can replace again this single rotation with some sort of self-testing and uplift it. That's interesting.
Thank you. Okay, one more thing. Actually, you considered, I think, graph states, right, for all this architecture. So if we extend this to, for example, stabilizer states, so will that help, or can it be extended in that way? I mean, without considering any graph, without
I don't
considering.
think, yeah, I don't think graph is anything particular. I mean, like, you can do this sort of MBQC. That's why I was saying, to me, it's not even important to do it necessarily in the measure-based quantum computing model. You can do it in even a quantum circuit model. The only thing that is very key for all of our components in this adaptivity structure, that your essentially teleportation is the key element. The only thing that allow us to do all this magic is the teleportation, computing via teleportation, that we are able to run a computation on the server give the outcome, and then we know how to correct the Pauli correction, go forward. So I think doing it in a circuit base, doing it in the different stabilizer base, doing it in a hypergraph state, as long as the key component of computation is teleportation gate, is doable. I have this conjecture that actually we should be able to even prove that if we don't have this mid-circuit measurement or this teleportation-based gadget, you're not able to do it, but it's not very easy to prove what you're not able to do. So if it was entirely unitary evolution, you're not able to do. But as soon as you're allowing to do CP map evolution using teleportation as a gadget, you can do it with different things. How is it help? I think I've learned a lesson. Anything can help because forever you can optimize. When you want to really implement this thing, saving even few qubits and a few construction could be useful. So maybe going via a stabilizer, you can come up with a more clever trapification technique that with the fewer shots, you can actually achieve a better detection rate. So I think there is always room for improvement.
Thank you.
There are questions in chat.
Okay, I can read it. If we think of the circuit-based computation in a distributive computing scenario, one method talked about is circuit cutting, exactly. How does circuit cutting preserve or reconstruct the effect of non-local gate and entanglement in such a scenario? And what are the limitations of this reconstruction compared to the true entanglement-assisted protocol? And are the classical and quantum resource overhead justify circuit-based quantum computing in a distributive scenario? So I would say it's a bit of like a previous question, that everything that you say, this is exactly without considering privacy or verifiability. You want to optimize. You want to optimize the number of links between the server. You want to optimize the architecture. And my answer is that no matter what you come, at the end, you have an algorithm that is written in a non-private and non-verifiable way in a distributed architecture. And all we're doing is that we take that one and we add our link to it. So in a sense, I would say it makes no difference. You come up with your best architecture that has optimized, you have done your circuit knitting, you have designed where the qubit need to set, etc. And once that is designed, instead of running it in the method that you used to run, which doesn't provide you privacy. We're running it using our method that now is adding some randomization. So that's my high level answer. But in details, it might be a better circuit cutting you can do. So maybe if you know that you want to reduce the number of links between this point and that point, we are starting to putting new constraint in your circuit knitting. I have not looked at that, but I feel if we are serious, maybe actually optimizing the architecture plus entanglement and all the component you were saying in your question, together with the component of the privacy, might give you a different compilation. These are like a compiling technique. It's a good point.
So, are there any more questions? Let me ask one last question. So, is the implementation of security easier in gate-based quantum computing or measurement-based quantum computing? Because your original protocol is for measurement-based.
I would say that as I was mentioning, is I don't see a big difference between gate-based model or measure-based model. As long as you allow in the gate-based model mid-circuit measurement and gate teleportation. So if you want to do gate-based model with the full unitary evolution, we don't know how to do blindness. I mean, in this nice way that we are saying. So the key component, we write everything in MBQC because it's a useful toolkit. The key component is have the gate-based model. In fact, my colleague Anne Broadway has written all of this protocol in the gate-based model with gate teleportation as a gadget. So they are equivalent. And in fact, when you're looking at a particular platform, maybe in the cold atom or in the photonic, they are easy to create this massive entanglement and then do MBQC style. Whereas in superconducting and ion trap, they are still much preferring to have the qubit-based model. So there is a very easy translation between two, but you need to have your gate-based, your teleportation and the mid-circuit measurement. These are the key components.
So, are there any more questions? Okay, then I think we should thank our speaker for enlightening us about this privacy and verification issues in distributed quantum computing. So let's thank our speaker again. Thank you.
Thank you very much for having me. Have a nice day. Bye.